Thank you everyone for sticking around for the end of a great, nice 2022. This is a joint effort by many colleagues at Sandia, including others I'd likely owe an apology to for not explicitly listing here. As we've been researching novel spiking algorithms and looking to the brain for computational insight, such as several colleagues have been presenting at this meeting, just like Felix presented right now, a reoccurring challenge has been how do we articulate or identify a neuromorphic advantage? You may be thinking, here comes yet another benchmarking talk. But I was careful to not even say benchmark in that opening. So let's get into why and what I am talking about. As the saying goes, all benchmarks are wrong, but some are useful. Conventional benchmarks are generally defined by the processing to be executed. This can be a kernel like an FFT or the well-known LinPack benchmark solving a system of linear equations. AI or ML benchmarks sometimes are a particular model. Take, for example, a ResNet 50 as a very common example. Or other times, the benchmark is defined by the data set, the task, like the well-trod MNIST. And so we have a little bit of a variation. There's flexibility where this flexibility offers an interesting twist where the valuable contribution may be the solution itself. So rather than being interested in the accuracy on MNIST, the interesting part may be how exactly did you compute that solution? So it's a little bit different than traditional benchmarks. But in that flexibility, what computation is being executed is, of course, it makes direct comparisons difficult, because if you're not computing the same thing on different approaches, different platforms, it makes it very difficult to cleanly compare one-to-one. And so as an extreme example that no one would ever do, but if we are working with MNIST, if you have a large vision transformer with hundreds of millions of parameters being computed, or if you have a small multi-layer perceptron or even just a regression model, those are very, very different. And it's hard to draw comparisons to them just based upon looking at how do they do the MNIST task. But regardless, you could argue the point to benchmarks is to articulate information for the sake of comparison, or phrased differently, the aspiration is to convey merit. And this is actually more difficult than you might naively think. Data-driven machine learning has readily proliferated domain and application-specific data sets. We have different classes to identify, we have specific sensor modalities, we have challenging conditions, we have a lot of different driving factors which are leading to more and more data sets viewed as benchmarks. And so there are even fun crowdsourced labeling efforts to apply labels to anything from Martian terrain to ancient manuscripts. It's a fun state of the world right now for AI and machine learning. However, many of these efforts arguably fall flat. In this recent effort by Adriano Barbosa Silva, they surveyed 1,688 benchmarks, creating a taxonomy of AI tasks, as well as looking at temporal trends. They have a nice website that you can get from their archive preprint that just came out about a month ago, where you can delve into the particulars of the models, you can play with dynamically the website's taxonomy. But shown here are two of their visuals for natural language processing and vision processing over time. Clearly, there's been a boon in benchmarks lately. However, 1/3 of them do not meet a simple threshold of being used at least 3 times. So in that sense, they convey some insight, but they're seemingly not readily being used for ongoing comparisons. And so at NICE, as the field of neuromorphic computing at large, our goal is not to just put out yet another benchmark, not to say here's the right benchmark, but rather to advance the field to garner insight and understanding. How can we not just make it a matter of here's yet another benchmark that'll live one day and be gone the next? And so if you're still with me through that buildup and motivation, the title slide already tipped my hand. We've looked to the field of high performance computing for best practices in what are called mini apps. Like benchmarks, they are small, self-contained programs. They capture performance-intensive computations, but importantly, more than just capturing the minimalist kernel or a small task, they capture the context of the computation. And in doing so, that offers several advantages. They can facilitate interactions between research communities. So as we talk about bridging between algorithms and architectures or vendors, it offers commonality that people can speak to, they can assess things with. In that regard, they can also enable assessing prototype nodes as well as exploring larger scaling. They can spur language and programming developments, general optimizations. And in that role, conventional systems have less uncertainty at the algorithm and programming level. HPC kernels and codes are more established. And so there's a larger role of using the mini apps, the known computations, to drive innovation in test beds. Whereas neuromorphic systems, you could argue, have much more uncertainty at the algorithm level, making a role for mini apps to help drive this research bottom up, so to say, at least with regard to this visual here on the bottom right, where we want to understand how algorithms are impacting architectures to then justify systems to then drive the next generation's platforms. This illustration relates the vision with the traditional HPC infrastructure on the left and the neuromorphic approach we've been pursuing on the right. Top to bottom, a suite of scientific computing mini apps can be mapped to a platform agnostic intermediate portable framework like Cocos and Raja, and then can be compared on large scale systems as well as simulation tools. We're proposing analogously for neural mini apps, which can be captured via a platform agnostic representation and then leveraged to understand trade-offs on different neuromorphic architectures. How do they perform on something like Intel's Loihi or University of Manchester Spinnaker? Before getting into our mini apps, as that intermediate, Fugu is a tool we've been developing over the last few years, striving to facilitate neuromorphic programming by combining two key ideas. First of all, component-based assembly of larger solutions from smaller solutions. In other words, composability. How can we build more sophisticated neural computations by combining smaller neural circuits? And also cross-platform portability. By representing neural algorithms in a common graph format, portability can be achieved by translating the graph representing nodes and edges or neurons and synapses into backend specific constraints. So to build algorithms in Fugu, Fugu establishes a minimalist neuron model, which we've tried to make compatible with many neuromorphic devices. So roughly, Fugu is capable of describing any of the features used in threshold gates, so fan in, fan out, a threshold, and synaptic weights. And then additionally, most features of spiking neurons, synapse delays, decay, and noise. A brick encapsulates a desired functionality, so it has well-defined inputs and outputs and some internal operation. And then scaffolds combine bricks to build algorithms. This framework is a Python tool where platform-specific code can then translate to neuromorphic backends. So for example, you might use NX Core for compatibility with Loihi. Here, we provide a code snippet to illustrate working with Fugu. Namely, this example is a binary streaming adder where 3 neurons whose thresholds and lateral activity and as well as their decays allow for the simple circuit to account for all possible binary input combinations. And so the left 2 yellow neurons, the denoted A and B in the top left figure, they serve as our input bricks. And so these are on lines 7 and 8 of the code snippet in the bottom left. And then the 3 blue neurons are the adder brick, which are encapsulated into line 9 of the code, and together this scaffold then has the 1 green output. And so while this isn't necessarily a computation you'd want to do with neurons, it does provide an illustration where you can understand the flow of spikes, neuron states, you can verify the correct Boolean output, and largely it's a simple enough example that I could put the code in the bottom left here so you can see what Fugu code looks like. So that brings us to our initial neural mini apps. Neuromorphic computing is potentially great at a lot of applications. It has a lot of potential. Our starting point captures a diversity of applications for which the community has identified neuromorphic advantages. So as has been presented at NICE, at ICONS, in the literature at large, we've been looking at common examples over the last decade or so. And I'm not going to go into the depth of the particulars and the theory behind these three, as each could be an extensive talk on its own, but rather I'm going to highlight how they articulate different facets of neuromorphic computing as a mini app, and then how they can how those insights can then be meaningful to the neuromorphic field. The first mini app focuses upon random walk methods for solving partial differential equations. You may have seen Brad Imeny and others present this in recent years as a scientific computing example. So it presents an example in scientific computing domain. Then within the machine learning domain, the second mini app is more so speaking to machine learning of today, sparse coding for image processing. And so this is a high bar given how prevalent GPUs and accelerators have been, but it kind of speaks to a realistic challenge. It shows a common problem being pursued. And then finally, a little bit more forward-looking, and what we're kind of talking of artificial intelligence of tomorrow, speaking to the promise of graph analytics, graph relationships as having a good fit for a lot of neuromorphic architectures. As a starting point, we're looking at shortest path on a graph, and I'll speak to that in a moment as to what properties that has for exploring computational costs. Here, we're simply trying to compare properties of the different initial neural mini apps. They're intentionally trying to highlight different facets that are important to neuromorphic computing. The idea being that by then comparing different apps, you can understand, is a particular neuromorphic platform good at all of these? Is it good at specific ones? Why? The color key here, the green columns, the first two columns, they capture computational properties that are largely attainable by threshold gates. The red columns then introduce features which are more explicitly neural as we start adding in synaptic delays, decays, random noise. And then as an aspirational, while we don't have anything in that final column under online learning yet, Fugu itself has hooks amenable for exploring learning. And we acknowledge it's a crucial property in the future of neuromorphic computing. So intentionally put it as a let's try to get there, even though we don't have anything right now. That being said, as this quantitative chart illustrates the different neural mini apps, showing how they leverage different computational principles and can stress neuromorphic architectures in different manners. Here, I'm simply showing the structure of how to work with a mini app in Fugu. It's via a command line interface. You can specify the mini app, you can specify computational backends, as well as mini app specific parameters. So in this example, we're saying we want to run the random walk mini app. We want to run it on Loihi. We can specify the number of simulation time steps, the number of walkers, and other parameters. As described earlier, the Fugu scaffold process composes the computational graph of the constituent bricks. And so it brings together the overarching computation. And then as illustrated in the bottom right cartoon illustration, these can then be mapped to different backends, including a reference CPU simulation. And then you can use this to try and help facilitate computational analysis, looking at different platforms, as well as how their respective platforms can handle scaling of the different mini apps. So briefly, as a real scientific computation, our neuromorphic random walk code describes diffusion via a discrete time Markov chain, which can compute particle angular fluence. In other words, how do particles scatter under various diffusion conditions? There's a great Nature Electronics paper, which Darby Smith, Brad Imeny, William Sverra, and others published that just came out fairly recently, that goes into the particulars of how the computation is done on neuromorphic, how you can cast the computation in neuromorphic forms versus traditional CPU form, the differences of that. But for the purposes of advocating for neural mini apps, importantly, I'd like to point out there are several parameters which can be tuned and scaling factors which can be analyzed. I say this in contrast to my earlier introduction of benchmarks. And so to bring this back to, well, is this just benchmarks by another name? A key differentiator is that with the common benchmarks, whereas a particular computation might be run and you get out how well your architecture compute, say a ResNet 50. Instead, here, these parameterizations and scaling allow you to explore changes to the fundamental computation. What size mesh are you running in this case? How many walkers do you have? Parameters of that impact the scientific code result. How does that change the result on the neuromorphic architecture? How does it scale? How does it run? How can we get more than just that singular data point of we ran a ResNet 50? As an example to this, on the right, we show curves where we're intentionally scaling properties and seeing the implication of that coupling with neuromorphic architectures. Namely, as we increase the number of mesh points, we're looking at how things scale on a Fugu CPU backend simulation, how it scales on Spinnaker, as well as how it scales on Loihi. As our second exemplar mini app, sparse coding or sparse dictionary learning. It's a way of modeling data by decomposing it into sparse linear combinations of elements of a given overcomplete basis set. And then when the dictionary's been learned, that sparse coding process is to find the sparse coding of the input vector using lateral inhibition through an LCA algorithm that's been previously presented. Again, this has several tunable parameters, such as the size of your input image, the size of your dictionary, sparsity levels, and by exploring how those impact an underlying architecture, you can explore what happens at different sparsity levels, different levels of communication. How does the problem parallelize? How does communication affect your result? For the example results shown here on the right, a weak scaling study increased the number of input patches to be reconstructed, keeping the dictionary size and the computational parameters fixed. That approach is embarrassingly parallel because the patches can be computed independently. And so the Spinnaker and Loihi plots on the bottom showcase much better parallelism than a traditional CPU-based effort using Fista and Lasso toolboxes on the top. Lastly, while graph analytics can capture many computations, here we've started with a well-known single source shortest path problem. It's computation as a straightforward mapping to neuromorphic where the path length between any two nodes equates to a delay. And so it can use temporal delays in a spiking neuromorphic architecture. Here, the mini app can be varied by using graphs of different types that have different connectivity structures, different numbers of nodes, different distances between nodes, and in a lot of ways we can see how does a neuromorphic architecture respond to sweeping over those properties. The vignette results shown on the right, again, they show scaling that's much better on Loihi and Spinnaker than CPU-based simulations. And so as I wrap up, going back to my original motivation about why mini apps, I'll reiterate the context of computation is important because not only does the context provide a more realistic assessment of the technology, but it can also capture the broader impact of where an advantage may come from more than just a minimal core computation. You need to factor in, are you having to do a lot of pre-processing, post-analysis? Let's look at more than just potentially accelerating and multiply and accumulate, but let's factor in what is the entire computation that we want to be able to achieve. Even if that means that you're doing part of that on an adjacent coprocessor or host system, let's look at the full context. Or even when a key computation can be performed efficiently, other factors can be limiting, and some of the Fugu design principles like compositionality and scale let us look at properties like we've shown here of let's look at rigorous physics simulation details. Let's make sure we're solving a real problem. And let's also take into account, as I say, a real problem, are we looking at something that's going to scale? That there's been research, such as the two examples shown on the bottom here, show that a neuromorphic advantage only may be under certain sizes, that if your problem is too small, you may be paying costs to set up your problem. And the neuromorphic advantages is once you get to a certain size. We need to understand when those wins, where those wins are. This can easily become semantics, but arguably benchmarking can fall short as being mere data from an architecture, whereas mini apps can yield data about an architecture, meaning that a benchmark might tell you how one application runs, but tuning parameters to understand when communication saturates or how things scale or when your architecture becomes overwhelmed, you could say that provides an understanding of the architecture. And so that might help us inform, is ResNet 34 the right architecture, the right algorithm for a given architecture, or is ResNet 50? Let's not assume that that answer is the same for every architecture, but let's understand why different algorithms map to different architectures efficiently. Given that neuromorphic architectures are being actively explored, mini apps for neuromorphic we see as an important contribution for understanding the architectures themselves and not just their performance to drive next generation designs. In closing, I've introduced Fugu as well as 3 neuromorphic mini apps. They span a diversity of applications and stress architectures in different manners. In doing so, by better understanding applications and not just minimal computational kernels, we can better articulate when and where there are neuromorphic advantages compared with traditional approaches. This is just the beginning. We want it to be a community endeavor, expanding to further mini apps. These 3 aren't the end all, but we're going to be able to, we would love to see the community provide additional mini apps. Let's integrate with multiple backends. Let's advance the technology stack. And we're open sourcing Fugu. It's going to be released on GitHub very soon. We were hopefully trying to get it pushed for today, but that didn't happen. So I had to tack in the coming soon last night, but we're hoping in the very, very near future, it'll be publicly available, and look forward to engaging the community with it.